Moving on to chapter 3, we're going to be looking at continuity. Something we intuitively know what it is, right? Maybe your teacher told you if you could draw this line, this blue line here, without lifting up your pencil, or if the function looks like it's in one piece, things like that, then it's continuous, but we never really defined what it was. With limits, for example, this limit here, I'm going to circle it in green. This point here didn't have to exist, or sorry, didn't have to be defined, right? And continuity, we bring that point back into the picture, as you probably may know. So, for example, if we have the function f of x equals square root of x. Well, what is f of 2? Oh, and I should mention, this function is defined for x being greater than or equal to 0. But what is f of 2? That is going to be an irrational number, right? Because f of 2 will give us square root of 2. Now, there isn't really a way we can write that as a decimal that's really helpful. Well, yeah, there's no conventional means as to how we can write that as a decimal, but we can obtain rational numbers that are get really close to square root of 2. So, for example, 1.4 squared is equal to 1.96. 1.96 is pretty close to 2. We can get even closer if we do 1.41 or 1.414, right? We're getting closer and closer to 2. So what's my point here? My point here is this is square root of 2 is right here. So this here is the square root of 2. My point is that as we get closer and closer to 2, our values get closer and closer to square root of 2. So this function is indeed continuous at square root of, or at f of 2, sorry. It's continuous, sorry, I should say at x equals 2. It's continuous. And that's not a proof. I'm just kind of building intuition here. As just as limits, the closer and closer we get to our point here 2, the closer and closer the values in the y-axis get close to our square root of 2. And we'll prove later that this function is indeed continuous at x equals 2. That does require a formal proof. We can't just say this and assume it's true. So we will define what a continuous function is. So suppose E is an R, and yes, this is a real number here. Suppose E is a subset of the reals, and the function f maps E to R. If x naught is an E, then f is continuous at x naught if and only if for each epsilon greater than 0, there's a delta greater than 0, such that the difference between x and x naught being less than delta and x and E implies that f of x minus fx of naught, that difference is less than epsilon. So really similar to a definition of a limit. And if f is continuous at x, for every x in the set, we say that f is continuous. The function is continuous. And before I start drawing pictures to kind of illustrate what's happening, I'm going to bring up the definition of a limit. So the definition of a limit here, if you remember, let f map d to r with x naught an accumulation point of d, then f has a limit L at x naught if and only if blah, 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 the rest. So what I really wanted to do is compare both of these definitions. What is different? What's the same? Well, I suppose I'll do red is different. What is different? And in blue, I'll do what is the same. So first thing I do want to point out, X not an accumulation point of D. Here, X naught only has to belong to E. It does not need to be an accumulation point of D. The only interesting case is when it is an accumulation point of E, but I'll go over that shortly. But that's a big difference. On the limits, X naught has to be an accumulation point. Here, it doesn't have to be an accumulation point. Now, what's basically the same? Well, this whole thing, the delta greater than 0, this difference implies this difference. Same thing over here, delta greater than 0, this difference has to be greater than or equal to this difference. Here, I should underline this in red actually. Here it says greater than 0. This doesn't have to be greater than 0. The continuity here, we don't have greater than 0 because it doesn't have to be greater than 0. It can be 0. And again, I'll go over that shortly. But it's basically saying the same thing. As we're getting, let's say X naught is here. If we're doing limits, and say this was our set D, well then X naught has to be an accumulation point, right? As our definition says over here. It has to be an accumulation point. If this was our set E, well, X naught does not have to be an accumulation point, not necessarily. And actually, let me bring in a picture to help us with this understanding. So I think this picture is better. So as you see here, the closer and closer delta, or the smaller and smaller we make our neighborhood, our delta neighborhood around X naught, the closer and closer this epsilon neighborhood gets close to f of X naught. So it's a lot like the limit definition. But now I want to go over that case where X naught isn't an accumulation point. Because again, definition of continuity doesn't require it for it to be an accumulation point. And let me show you that that case is not interesting. And I'll show you what that means, what I mean by not interesting. So let's say X naught here is not an accumulation point. Right? So that means that this here, I should eliminate this. So what did I just do? I erased the points really close to X naught. It's an isolated point. I know we haven't gotten over the proper definition of an isolated point, but an isolated point is a point that's not an accumulation point. So if it's all on its own, well then that means that this function over here, I should delete this as well. Let me delete it with the white, because the function isn't defined for those x values, so these shouldn't be there. Okay, so that's how our function looks if x naught isn't here is not an accumulation point. Is the function continuous at x naught? Well, it is, and I'll show you why. Let's say this is the neighborhood. I'm gonna here, and then let's say over here. Well, here, why is it continuous at this point if it's just an isolated point? Well, because if we chose this neighborhood here, this delta neighborhood of x naught, well, x naught is the only point. This is the only point in the neighborhood. N hood, all right, in the neighborhood, in the delta neighborhood. Right, that's the only point. So in this case, over here, using the definition, x minus x naught. Well, x has to be an e, and e here is our little neighborhood. E is our delta neighborhood. What points are in E? Well, just x naught, right? So x, for it to be an E, x has to equal x naught. And what's the difference between x and x naught? Oh, sorry. Difference between x and x naught? Well, since there's the same point, it's 0. Right? So what does this mean? This means that f of x minus f of x naught, well, there's the same point as well, is equal to 0. And that 0 is less than epsilon. And epsilon has to be greater than 0, right? So that's how we guarantee that it's less than epsilon for any epsilon. Right? Meaning that if it's an isolated point, as I just said, or the only point in the set E, then x naught has to equal to x, implying that their difference is 0. So then over here we get the f of x minus f of x naught is equal to 0, which is less than epsilon. So it's always less than epsilon. So our continuity, what is it? Our blinking out. Our continuity condition, or not condition, requirement. The requirement for a function to be continuous is always met because it's equal to 0, and that's always less than epsilon. Therefore, if a point is not an accumulation point, well, it's always continuous at that point. Now you may be wondering, well, this doesn't look like one piece, right? There's one piece, two pieces, three pieces, right? That doesn't look like a continuous function. Well, these points down here are never defined. So they're not necessarily breaking continuity because that doesn't even exist, right? Those points don't even exist. They're not defined for those points. So they're not really keeping the function from being continuous. And I know this kind of goes against some intuition of what we thought continuity was. But again, maybe we've been done a disservice when we were taught that our domain was all the real line. Sometimes it could just be, some certain sets of the real line, certain subsets of the real line. But those points aren't defined, so they don't prevent this function from being continuous. So just to phrase it one last time, I guess I could write it up here. If x naught is not an accumulation point of E, and x naught is in E, well then our function, I'm just calling it f, is continuous at x naught by default. Right. So again, just like any definition, continuity is really important. Kind of like stare at the definition, make sure you understand it, try to reproduce it, try to rewrite it yourself, see what you're missing. Also compare it to the limit definition. And you should see that those two definitions are almost identical, except for a few things which turn out to be really important. And in fact, that's why we go over limits first. In calculus here, we need limits to go over continuity and then over derivatives, integration, so on and so forth. But now we can go over just one theorem, and we're actually done with this section. That's just kind of introducing continuity. But this theorem, before we introduce the theorem, we're going to need this lemma. This theorem we went over a previous section. So if we let, I think it was section 2.2 or 2.3, I'm not remembering. But if we let f map d to r, with x naught an accumulation point of d, then f has a limit at x naught if and only if for each sequence xn converging to x naught with xn part of d and the terms of the sequence not equal to x naught, and the sequence f of xn also converges. Right, so all that's saying is, let me just draw a picture for that. This is our little function here. This is x naught. This is f of x naught. All that's saying, if you remember, is if we make a sequence that gets arbitrarily close to x naught, well then there's a sequence over here that gets arbitrarily close to f of x naught as well. Okay, so this is a theorem that's kind of a first of its kind. You'll probably see this in other classes if you've taken, or you will see it in your, maybe if you take topology or the next analysis class. It says let f map E to the reals with x naught in E and x naught in accumulation point of E. Well, then 1 through 3 are equivalent. So if f is continuous at x naught, that implies that f has a limit at x naught, and that limit, as x goes to x naught, of f of x happens to be f of x naught. So this one implies this one. Now, if we have 2 that's true, it'll imply this one for every sequence xn converging to x naught with xn in E for each n, then f of xn also converges to f of x naught. So the second implies the third, and also if you have the third, well, it implies the first one. So if we have this, I guess like series of implications, this one implies this one implies this one, 3 implies 1, then they're all equivalent. And we're going to prove this. So first we're going to prove we're going to prove that 3 implies 2. Right? So we're actually going to assume this. I should write up here. Assume 3, or not 3. I should write it in, be consistent. Assume 3 to prove 2. So we start off with assume 3 holds, right? Meaning that if xn converges to x naught, then f of xn converges to f of x naught. And this is where we're going to use our theorem. By the lemma above, f has a limit at x naught, and that limit happens to be f of x naught. Therefore, 3 implies 2. So we just basically use the lemma to show that 3 implies 2. And like I said, as the sequence x sub n gets closer and closer to x naught, well then on the y-axis, f of xn get closer and closer to f of x naught. Therefore, we get 2, that f has a limit at x naught, and that limit is precisely f of x naught. So that was a pretty straightforward proof. Now we're going to show that 2 implies 1. So I'm going to erase this, and we're going to say assume 2 to prove 1. So assume two holds. So by the limit definition, we're going to bring in epsilon. So assume choose epsilon greater than 0. Since two holds, right, since there is a limit at that point, well, then there is a delta greater than 0, such that if 0 is less than the difference between x and x naught, and that's less than delta, well, then the difference between f of x minus f of x naught is less than epsilon. And we're just getting this from the limit definition up here. Oh, f has a limit at x naught. This is where we're getting this. We're just stating the definition. This is what we have. This is the tool we have. So we're going to choose that. So we're going to show that one is true. So the only fact needed to fulfill the definition of continuity at x naught is to remove the condition that x minus x naught is greater than 0. Right? Because like I said before, the limit definition is extremely similar to the continuity definition, but there is a difference that in the limits, this difference has to be greater than 0. So we need to remove that condition for it to be continuous. Right? Well, let's take the case where x minus x naught is equal to 0. Well, then that means that x is equal to x naught. And as we had seen before in the last slide, f of x minus f of x naught is equal to 0, which is always less than epsilon. So by default, f is continuous at x naught. In other words, 2 implies 1. I may have, you may have to rewind some parts and kind of see what's happening slowly, because analysis isn't typically a class where you just see the lesson for the first time and understand it. It really takes some digesting. So now we're going to suppose 1 holds, and we're going to show that this implies 3. So now I should write up here, assume 1 to prove 3. So choose epsilon greater than 0, because we're assuming f is continuous at x naught. Well, then there's a delta greater than 0, such that this is that difference is less than delta, and x is an e, then this difference is less than epsilon. And again, that's just stating the definition of continuity. This is just a definition of continuity, which we're getting by assuming the first one, right? F is continued at x naught. Well, if f is continued at x naught, since x sub n converges to x naught, right? Because we're supposing this, xn is a sequence of points that converges to x naught. We need to show that f of x n converges to f of x naught. Well, for n big enough, f of xn minus f of x naught is less than epsilon. Now we're bringing in the definition of sequence, of convergent sequences, right? Because this sequence converges, let me erase here. Because this sequence here converges to x naught, there's an n greater than big N, such that this difference is less than epsilon, right? Definition of convergence. Well, that just means that f of xn converges to f of x naught, right? This little thing here is telling us, by definition of convergence, that f of xn does converge to f of x naught, because their difference is less than epsilon after n is greater than or equal to n. So again, that's how we get this conclusion, and we just showed that if we assume 1, we get to prove 3. So therefore, we just went in our circle. So this implies 3 implies 2, 2 implies 1, 1 implies 3, showing that all these statements are indeed equivalent. Again, continuity is extremely important. This chapter is only going to get harder, so make sure you do have this definition digested, see how this works, get this theorem in your head, because we might use different, for some proofs, we might use the first definition of continuity or the second one, or the third statement. Right? They're different tools, essentially the same tool, but in different forms that can help us prove certain theorems easier. And that's it. That concludes this section.